This week we want to do it slightly different. I would like to start off with just walking everybody through the workflow of image-to-image processing. That's either image to segmentation or image to regression type of workflows. These are very similar. And that will take me about 10 to 15 minutes. In the meantime, you can already post any questions that you have to us, the panel. So the panel consists of me, Paul de Groot, my colleague Hardeep Jaklan, and Arno Huck. And we'll try to answer any questions after the walkthrough. So let me start by showing you OpenDetect and the dataset that I would like to talk you through. So I'll minimize a few things. Okay, this is my dataset from the city of Delft. And it's just a small seismic kubelet that I'm using for experimentation. And this is the city of Delft. Famous university is over here. And what we have is 3D seismic. And I did some manipulations. So I interpreted a couple of horizons. And then I created a couple of data sets, synthetic data sets that I want to use for training. And then I want to apply my trained convolutional neural network, because that's what I'm going to do, a Unet. I'm going to apply it on the real seismic. So I want to transform this 3D seismic cube into something else. And I'm doing that in a roundabout way by first creating synthetic data. And I'm doing that because I want to have full control over what is input related to target output. Obviously, if you have real seismic data and sufficient examples, and you know exactly that this input belongs to that output, then you don't need to do it through synthetic data, but that's not always the case. That's one of the problems that we have in seismic applications. And that is one of the reasons why we often refer to synthetic data, because then we know exactly what belongs together. And then we hope that once we train a model, we can apply it to the real data, and the outcome is then hopefully useful. So what I did in this particular case, I did 2 workflows, and these workflows are described in the machine learning user doc. One is to transform seismic into classes, intervals, 1 until 8, and the classes are marked here by 1, 2, 3, and so on in between the mapped horizons. So that is an image to segmentation type of problem. And in the other example, I try to convert the seismic into relative geologic time. And the relative geologic time was created also in a synthetic way using a model-driven horizon cube type of approach. Now, all that kind of manipulations, that is what you can do in OpenDetect, and I'll just show you some of the basics on how I actually created the synthetics. And that is just as an example. You don't have to try and emulate this, because eventually this was an experiment, and I used that experiment to describe the workflow in the user doc. But unfortunately, the output is not really all that useful, neither for the segmentation result, and especially not for the workflow that aims to predict relative geologic time, because that is a very difficult problem. Anyways, so what I did first is I have 2 wells in this case. So I have acoustic impedance well logs. These are shown here. I used the volume generator. So this tool here to create acoustic impedance volume, a synthetic acoustic impedance volume. And that volume is basically just interpolating in between these wells and following the the timelines created in between these horizons. So it's a model-driven type of interpolation. Now that's nice, but normally we don't have acoustic impedance. We have seismic data. So I then transformed the acoustic impedance into synthetic seismic. And that is my synthetic seismic cube. And this obviously I can use because that looks like real seismic. It's only 2 wells, so it's a bit synthetic and not all that beautiful. But anyway, it has some resemblance to real seismic, and that's why I'm using this. And that could be used as an input for my model. And then I have to also define an output. And the output in this case was created by calculating a classification number, an interval between these horizons. And that took me just some attribute manipulations in the attribute set. You can quite easily do that. So I created numbers from 1 until 9 to subdivide this whole cube into a synthetic cube with just intervals. And the aim of the whole game in this case is to go from the synthetic seismic to these classification cube. And if I can do that and the model is trained, I want to apply it to the real seismic and to see what comes out of this. And then hopefully I get also nice classification results from the real seismic. Now, in order to not completely cheat my way all the way through the entire exercise, you see this green line here. I'm using approximately half of the cube, the part in front of me, for creating my examples. And I'm applying the trained network on the real seismic to the entire seismic volume. So the data seen to the north of this green line was never seen by the neural network, not from the synthetic data, and that could then be regarded as a true blind test. Okay, now let's see how we do this. I'm going to use this workflow, seismic image segmentation. So you go from some kind of, in this case, 3D volume, a 3D seismic cube as input. You also need a 3D segmented volume as output. So I'm doing go, and this opens the next tab. And as we have seen from the machine learning, it always consists of 3 tabs. There's a way to extract data, then there is the training on the extracted examples, and then there's the application phase. And we're just going to walk through this. So first I need data, and I've already done this, so I'm going to go through these steps again. I'm going to select, pressing this plus button, new data from this survey. So the software allows me to select data from multiple surveys. And in this case, I select the seismic Delft survey that I'm working on. And what I want to get out is the classification cube. So that is the 1, 2, 3, 4 until 9 different classes. I also want to select that only the first part of the data, so the inline range from 2500 to 2750, will be used for training examples. And I only have data in my synthetic data set above 2 seconds. This is 2 seconds. Okay, and now I'm going to say okay. And now I could go into other surveys, other examples, and extend this, but I'm not going to do that because I'm working only with 1 cube. So I'm going to press proceed, and from here I can select multiple input cubes. Now, obviously the input cube is my synthetic seismic cube, but I'm also selecting a second cube. I'm selecting the 2-way time, so I have created a volume with just time values from 0 to 2 seconds. And I'm doing that because when I'm extracting my data, I will extract small images, and it will help the network to know whether this image was extracted somewhere above or somewhere deeper down or somewhere in the seismic relative to the depth range, because there is a kind of ordering in this classification, and that will therefore logically make some sense. So I will have two input volumes, and these are given here, the synthetic seismic and the Z volume. And here we see what we are going to extract. So in this particular case, I'm extracting everything along inlines, and in this case only 2D images, 128 samples by 128 samples. And you can see here how many examples I'm extracting from this cube in the range from 2500 to 2750. If I want to, for instance, do 3D seismic cubelets, which is also possible, I could extract here 128 by 128 by 128. But if I do that, then in this range of my data, I will have only 147 examples. So that is not really helpful. That is not enough. So I'm going to do it just like this as 2D images. I have 12,900. You also see here the overlap. That means that I will have images extracted with 50% overlap in this cross line. So I can have 7 of these images in each cross line before I'm running out of my cross lines. If I would do this with 0, no overlap at all, I can only extract 4 of these. And you see my number of examples drops. So what you want to have is you want to have sufficient number of examples to do this type of training. And I think at least 10,000, 20,000, 30,000, up to 100,000 seems to be quite normal. Now then you give it a name. This will be your example data set. And I'm not going to do that because if I do that, it will extract all these images. And I've already done that, so I'm going to close this. I'm going to close this, and I'm going to show you the actual example set. So here is the result again of this data set that I've extracted in this way. Next to it, you see 2 icons. One is a management icon. So here I can rename data, I can throw it away, and I also see information on how this particular data set was created, where it came from, when I created it, and so on. So that this icon is important. You will see it many places in the user interface. The other icon is also useful. It's a viewer. It allows me to view what kind of data I actually have extracted from the data and what the problem I'm trying to solve actually, how I'm going to present this to the network later on. So this is my input. I'll zoom it a little bit, make it a little bit bigger. And I'll jump to a more interesting image. Okay, so what you see here is an example. In this case, example number 4,548 from my set, with the seismic as input and the target as output. So this is a segmentation problem, so that's why we have segmented results numbers 1 until 9 below. And that is what my network, my segmentation network, needs to learn. Okay, image to image processing we do in Keras TensorFlow, and we can select the kind of parameters. We only have a Unet segmentation network in this release, so that is the network that we will train. The batch size depends on how many examples you can feed to the network, and that depends on how much memory and GPU memory you have. It's better to have a larger batch size than 4, but it didn't fit into my laptop, so that's why I have a very small number here. The number of epochs is how often we are going through the entire training cycle, training data sets. So we do that 15 times. The model, when we train it, will automatically be split into a training and test set. The patience is a number that allows me to let it train a little bit longer. So if it doesn't update after so many cycles, then it will automatically stop. But with a larger patience, you can continue to train it, and that helps. This is the learning rate, which is an important parameter to play with if the network doesn't converge. And you can either train on the GPU or on the CPU, depending on whether you have enough GPU capacity. Now, when you start training, you press this button, Run, and then that will start a log file. And that log file, here we actually see the result of my training, which was finished just before. So this is what I will show you later, what we actually did. The training will output information during training about the loss and the accuracy. And these numbers, they should go down and up. Now, that goes per epoch. And then after 15 epoch, in this case, it dumps the entire model. It says it has been trained successfully or not, and it has saved the model. Apart from seeing this information in this log file, which is started from here, it doesn't always start automatically. If it doesn't start, you just have to press the button, and sometimes you have to press reload to get an update of the log file. Apart from this log file, OpenDetect also automatically starts Tensorboard. And Tensorboard is an application that runs in a browser. And it gives you all kind of information on the model that you are currently running. So this is our Unet. It's a huge network. But the most important information are these scalars, which actually give you the accuracy and the loss functions for training and test data sets, validation sets. And these should go, the loss should go down, the accuracy should go up. And when that is flattened off, you have your trained network. Now that information is also useful because if you still see the thing might even go higher, then you could later, after the network was saved, pick that saved network up again and retrain it to continue and even get a better result. Now going back to this, so I'm not going to train this. This took me about an hour or so to actually train it on this machine. I'm going to show you the apply part. Here you pick up the trained model, you press proceed, and then it will ask you for the input. In this case, I would select the real seismic as input. I would also select the Z cube, which I created, and so the time cube. And then I would give it some kind of output. So this would be my unit classification output. Whatever I type here, that will be the output volume. Important parameters are these apply overlap. 10, 10, 10 means that on every side of the image, I will have an overlap in the application phase of 10 traces, 10 samples, and that will be smoothed out by the software. In the current release, that is not really happening yet, but in the next release, the next patch release, we will smooth this out nicely. And you can set whether you should run it on the GPU or CPU, and then off you go. Now, what is the result in this case? Let me just close all this. When I applied this, then the classification looked like this. So that looks quite reasonable, but remember that until here, this green line, I used examples from the input, also from the synthetic data. So synthetic and seismic, real seismic, seems to be working quite nicely. But when I then continue into the unknown, you can see it gets worse and worse, and I'm starting to lose my classification result. And that is especially, you can see that here on this cross line, which is already in the unknown part, the classification is not really that good. So this is not a brilliant result. It shows that we can use synthetic to do some classification on the real seismic. But the synthetic seismic is not representative for our application everywhere. And that's why we lose the predictability here. Now, the same workflow you can do for regression type of problems. So this is when you go from, for instance, acoustic impedance to porosity. That would be regression. You have both quantifiable numbers of the input as well as the desired output. And what I did in this case, I wanted to predict relative geologic time. So I know the relative geologic time. I created this myself from the model-driven synthetic time output. And then when I apply it to the real seismic, I'm hoping that I'm getting real geologic time predicted by the model. And that is not that good, as you can see from here. It's basically a not very useful result, but it shows you that the workflows are there. You can use it. You can use either 2D type of image-to-image regression problems or classification problems, or 3D couplet-to-couplet type of things. And it depends on what you are putting in and how you create your training sets and do your proper validations, whether you get a good results or not. This is what I wanted to show. So I would like to open up the floor now for questions.